The solid-state magnetostrictive system of Annis and Eberly. Theodore Annis and Patrick Eberly have produced a variation on this multiple magnetic path method, which is shown in their U.S. patent application 20090096219. They have opted to use a motionless reluctance switch, which is a solid-state device which can block magnetic flow when energized. They have arranged one of their devices like this. The ring shown in gray is a magnet which connects to the ring shown in yellow through two diagonal reluctance, magnetic flow, switches. The yellow ring can carry magnetic flux, and the control box marked 118 switches the diagonal strips on and off in turn, causing the magnetic flux to reverse its direction through the yellow ring. The coils wound on the yellow ring pick up this reversing magnetic flux and pass it out as an electric current. While only one pair of rings are shown here, the design allows for as many rings as are needed to be connected together as shown here. The patent says, the currently preferred motionless reluctance switch is described by Toshiyuki Ueno and Toshiro Higuchi, in their paper entitled Investigation of the Dynamic Properties of a Magnetic Flux Control Device Composed of Laminations of Magnetostrictive Piezoelectric Materials, University of Tokyo 2004. As shown in Fig. 4, this switch is made of a laminate of a giant magnetostrictive material 42, a terbium dysprosium iron alloy, bonded on both sides to a piezoelectric material 44, 46 to which electricity is applied. The application of electricity causes the reluctance of the piezoelectric material to increase. This original patent application is included in the appendix. However, very interestingly, there is another, completely different patent application from Annis and Eberly, with the same publication date and the same number. It is not at all obvious to me how that could be, but here is the bulk of that other patent application, the original being in the appendix. Energy generation apparatus and methods based upon magnetic flux switching. Abstract. In an electrical energy generator, at least one permanent magnet generates flux and a magnetizable member forms the single flux path. An electrically conductive coil is wound around the magnetizable member, and a plurality of flux switches are operative to sequentially reverse the flux from the magnet through the member, thereby inducing electrical current in the coil. A figure of 8 construction comprises two continuous loops of magnetizable material sharing a magnetizable member common to both loops. An alternative configuration uses stacked loops and a separate piece of material acting as the magnetizable member. One end of the magnet is coupled to one of the loops, with the other end being coupled to the other loop. Each loop further includes two flux switches operated in a 2x2 sequence to sequentially reverse the flux through the magnetizable member. A relatively small amount of electrical power is used to control the magnetic flux of a permanent magnet by switching the flux between alternate paths. The resulting power from the switched magnetic flux yields substantially more power than the power required for the input switching. Description. Field of the invention. This invention relates generally to energy generation and, in particular, to methods and apparatus wherein magnetic flux is switched through a flux path to produce electricity. Background of the invention. Magnetic flux may exist in free space, in materials that have the magnetic characteristics of free space, and in materials with magnetically conductive characteristics. The degree of magnetic conduction in magnetically conductive materials is typically indicated with a BH hysteresis curve, by a magnetization curve, or both. Permanent magnets may now be composed of materials which have a high coercively, Hc, a high magnetic flux density, Br, a high magnetomotive force, mmf, a high maximum energy product, Bhmax, with no significant deterioration of magnetic strength over time. An example is the neodymium iron boron permanent magnet from VAC of Germany, which has an Hc of 1,079,000 amperes per meter, a Br of 1.427 Tesla, an mmf ranging up to 575,000 ampere turns, and a Bh max of 392,000 joules per cubic meter. According to Moskowitz, Permanent Magnet Design and Application Handbook 1995, page 52, Magnetic flux may be thought of as flux lines which always leave and enter the surfaces of ferromagnetic materials at right angles, which never can make true right angle turns, which travel only in straight or curved paths, which follow the shortest distance, and which follow the path of lowest reluctance, resistance to magnetomotive force. Free space presents a high reluctance path to magnetic flux. There are many materials which have magnetic characteristics similar to those of free space. There are other materials which offer a low or lower reluctance path for magnetic flux, and it is these materials that typically comprise a defined and controllable magnetic path. High-performance magnetic materials for use as magnetic paths within a magnetic circuit are now available and are well suited for the rapid switching of magnetic flux with a minimum of eddy currents. Certain of these materials are highly nonlinear and respond to a small applied magnetomotive force, MMF, with a robust generation of magnetic flux, B, within the material. The magnetization curves of such materials show a high relative permeability, or, until the knee of the curve is reached, at which point or decreases rapidly approaching unity as magnetic saturation, BS, is reached. Some of these nonlinear, high-performance magnetic materials are referred to as square due to the shape of their BH hysteresis curves. An example is the FINEMET registered feet, 3H nanocrystalline core material made by Hitachi of Japan. Other examples include Superperm 49, Superperm 80, Supermalloy, Supersquare 80, Square 50, and Supermender, which are available from Magnetic Metals in the USA. A reluctance switch is a device or means that can significantly increase or decrease, typically increase, the reluctance of a magnetic path. This is ideally done in a direct and rapid manner, while allowing a subsequent restoration to the previous, typically lower, reluctance, also in a direct and rapid manner. A reluctance switch typically has analog characteristics. By way of contrast, an off/on electric switch typically has a digital characteristic, as there is no electricity bleed-through. With the current state of the art, however, reluctance switches exhibit some magnetic flux bleed-through. Reluctance switches may be implemented mechanically, such as to cause keeper movement to create an air gap, or electrically by various other means. One electrical reluctance switch implementation uses a control coil or coils wound around a magnetic path or a submember that affects the path. U.S. Navy publication, Navy Electricity and Electronics Series, Module 8, Introduction to Amplifiers, September 1998, page 3-64 to 3-66 describes how to modulate alternating current by changing the reluctance of the entire primary magnetic path by these means, one of which is used in a saturable core reactor and the other in a magnetic amplifier. Flynn, U.S. Pat. Number 6246561, Patrick E.T. Alabama, U.S. Pat. Number 6362718, Pedersen, U.S. Pat. Number 6946938, Marshall, and U.S. Patent Application 2005/01256702, A1. All disclose methods and apparatus that employ this type of reluctance switch for switching magnetic flux from a stationary permanent magnet or magnets for the purpose of generating electricity, and/or motive force. Another electrical means of implementing a reluctance switch is the placement within the primary magnetic path of certain classes of materials that change, typically increase, their reluctance upon the application of electricity. Another electrical means of implementing a reluctance switch is to saturate a subregion of a primary magnetic path by inserting conducting electrical wires into the material comprising the primary magnetic path. Such a technique is described by Conrad and Brudney in an improved method for virtual air gap length computation, in IEEE Transactions on Magnetics, Volume 41, Number 10, October 2005. Another electrical means of implementing a reluctance switch is described by Valery Ivanov of Bulgaria on the website www.inkomp-delta.com, shown in Fig. 1. An electric toroid 110 is inserted into a primary magnetic path, 100. So that the primary magnetic path is divided into two subpaths 110A and 110B. A net magnetic flux reduction effect in the primary magnetic path 100 results from the combination of the effects in the two subpaths 110A and 110B, each of which results from different physics principles. In the first subpath 110A, the magnetic flux generated by applying electrical current to the windings 110 around toroidal path 110 opposes and subtracts from its portion of the magnetic flux 103 received from the primary magnetic path 100, yielding a reduced magnetic flux, which is also further reduced by a decrease in the subpath 110A's relative permeability, thereby increasing the reluctance of the subpath. In the second subpath 110B, the magnetic flux generated by applying electrical current to the toroid windings 111 adds to its portion of the magnetic flux 103 received from primary magnetic path 100, yielding an increased net magnetic flux that approaches or exceeds the knee of the material's magnetization curve, thereby reducing its relative permeability and increasing its reluctance. Summary of the invention. This invention is directed to methods and apparatus where magnetic flux is switched in both direction and intensity through a flux path to produce electricity. The apparatus broadly comprises at least one permanent magnet generating flux, a magnetizable member forming the flux path, an electrical conductor wound around the magnetizable member, and a plurality of flux switches operating to reverse sequentially the flux from the magnet flowing through the member, thereby inducing electrical current in the coil. The preferred embodiment includes first and second loops of magnetizable material. The first loop has 4 segments in order A, 1, B, 2, and the second loop has 4 segments in order C, 3, D, 4. The magnetizable member couples segments 2 and 4, and the permanent magnet couples segments 1 and 3, such that the flux from the magnet flows through segments A, B, C, D and the magnetizable member. 4 magnetic flux switches are provided, each controlling the flux through a respective one of the segments A, B, C, D. A controller is operative to activate switches A, D and B, C in an alternating sequence, thereby reversing the flux through the segment and inducing electricity in the electrical conductor. The flux flowing through each segment A, B, C, D is substantially half of that flowing through the magnetizable member prior to switch activation. The loops and magnetizable member are preferably composed of a nanocrystalline material exhibiting a substantially square BH intrinsic curve. Each magnetic flux switch adds flux to the segment it controls, thereby magnetically saturating that segment when activated. To implement the switches, each segment may have an aperture formed through it and a coil of wire wound around a portion of that segment and through the aperture. The controller may be at least initially operative to drive the switch coils with electrical current spikes. The first and second loops may be toroidal in shape, and the loops may be spaced apart from one another, with A opposing C, and 1 opposing 3, and with B opposing D and 2 opposing 4. The magnetizable member in this case is preferably a separate piece of material. Alternatively, the first and second loops may form a figure of 8 shape, with the 2 loops intersecting to form the magnetizable member. The permanent magnet, S, and the material comprising the magnetic paths are preferably proportioned such that the material through the common segment is at or slightly below its maximum relative permeability before the electrically conducting output coil is energized. In the preferred embodiments, the power resulting from the switched magnetic flux yields substantially more power than the power required for the input switching. Brief description of the drawings. Fig 1 is a drawing of a prior art reluctance switch in the form of an electrical toroid inserted into a primary magnetic path. Fig 2 is a detail drawing of a reluctance switch according to the invention. Fig 3a and Fig 3b are detail drawings showing the use of 4 reluctance switches according to the invention. Fig 4 is a drawing which depicts a preferred embodiment of the invention. Fig 5 is a detail drawing an alternative reluctance switch according to the invention implemented through split laminations. Fig 6a and Fig 6b show the operation of an energy generator according to the invention. Fig 7a is an exploded view of a preferred energy generator construction. Fig 7b is a side view of the construction shown in Fig 7a. Fig 8 is a simplified schematic diagram of components used to simulate the apparatus of the invention. Fig 9a is a diagram that shows the current delivered to one pair of flux switches in the simulation. Fig 9b is a diagram that shows the current delivered to the other set of flux switches in the simulation. Fig 10 shows the output of the simulation shown here, and Fig 11 is a block diagram of a controller applicable to the invention. Detailed description of the invention. Fig 2 is a detailed drawing of a reluctance switch according to the invention. The reluctance switch includes the following components: a closed magnetic path 110 comprised of a high-performance magnetic material, preferably a nonlinear material exhibiting a sharp knee as saturation is approached, around which is wound a coil 111. The closed magnetic path 110 shares a common segment 101 with a primary magnetic path 100, in which magnetic flux 103 is induced by a permanent magnet, shown in subsequent drawings. Electric current is applied to windings 111 having a polarity and sufficient amperage so that the magnetic flux generated in the path of switch 110 is additive to the magnetic flux 103 from the permanent magnet, such that the primary path 110 approaches or reaches magnetic saturation. Fig 3a and Fig 3b are detailed drawings of an apparatus which employs 4 reluctance switches according to the invention in a manner similar to that disclosed in U.S. Patent Application Serial No. 11/735, 746 entitled Electricity Generating Apparatus utilizing a single magnetic flux path, the entire content of which is incorporated herein by reference. In this and in all embodiments described herein, the geometry of the closed magnetic paths may be circular, toroidal, rectangular, or any other closed path shapes. A primary path 304 carries the flux from permanent magnet 302 unidirectionally. Flux switch pairs 310A/E and 310B/D are activated in alternating fashion to reverse the flux in magnetizable member 304C, thereby inducing electrical current in winding 330. Fig 3a shows the flux flow in one direction, and Fig 3b shows it reversed. In Fig 3a, switches 310A and 310E are activated by controller 320 in electrical communication with the windings on the switches such as through conductor 322 to winding 324. The additional flux in switches 310A and 310E are additive with the flux that would otherwise be present in segments 304A and 304E, thereby saturating these paths, causing the flux through segment 304C to be in the direction shown. In Fig 3b, switches 310B and 310D are activated, saturating segments 304B and 304D, and reversing the flow. Fig 4 is a drawing that depicts an embodiment of the invention using circular toroids 400, 401 and multiple permanent magnets 402, 403 disposed in the primary path 404. The two toroids 400, 401 intersect, forming magnetizable member 404E. A coil 430 is wound around the member 404E, as shown. The primary magnetic path 404 interconnects the upper end of loop 400 and the lower end of loop 401. One of the magnets, 402, couples one end of the primary magnetic path 404 to the first loop 400, and another, 403, couples the other end of the primary magnetic path 404 to the second loop 401. In this, and all of the embodiments described here, the permanent magnets are strong, rare earth magnets, and multiple magnets of any length, thickness, may be used in each case. Further, in all embodiments, the loops, primary magnetic path and / or magnetizable member are preferably constructed from a high magnetic permeability material such as the FINEMET feet, 3H nanocrystalline soft magnetic material available from Hitachi. The invention is not limited in this regard, however, as alternative materials, including laminated materials, may be used. The connections of the primary magnetic path 404 to the 2-loop 401 create 4 segments apart from the magnetizable member 404E, the 4 segments including 2 opposing segments A, B in the first loop on either side of magnet 402, and the 2 opposing segments C, D in the second loop on either side of magnet 403. 4 magnetic flux switches are provided, each being operative to control the flux through a respective one of the 4 segments. A controller 420 is operative to activate the switches associated with segments A and D, and then B and C, alternately, thereby reversing the flux through the member 404E, and so, inducing electrical current in coil 430. Apertures may be formed through each of the 4 segments, with the switches being implemented by coils 410A to 410D which pass through the apertures and around an outer, or inner, portion of each segment. As shown in Fig. 5, if the loops are fabricated with laminated material 502, the laminations may be split at 506 to accommodate coil 504. The percentage of the segment surrounded by the coil may vary in accordance with the material used. The waveforms presented to the coils, and other factors, with the goal being to magnetically saturate each segment through activation of the associated switch, thereby reversing the flux through path 404E. Fig 6a and Fig 6b show the operation of the apparatus of Fig 4. The primary path 404 carries the flux from permanent magnets 402 and 403 unidirectionally. Reluctance switches 410A to 410D are activated alternately to reverse the flux in segment 404E which, in turn, induces electrical current in winding 430. Fig 6a shows the flux flow in one direction, and Fig 6b shows it flowing in the opposite direction. In Fig 6a, switches 410A and 410D are activated by controller 420 in electrical communication with the windings on the switches, such as through conductors 422 to switch 410B. The flux provided by switches 410A and 410D, thereby saturating these paths, causing the flux through segment 404C to be in the direction shown. In Fig 6b, switches 410B and 410C are activated, saturating segments 404B and 404D, thereby reversing the flux through path 404E. Fig 7a depicts a preferred construction of the apparatus depicted in Fig 4, Fig 6a and Fig 6b. Loops 400 and 401 are implemented as complete toroids 700, 701. This is important, since preferred high-performance magnetic materials are currently available in regular shapes of this kind. Note that, in this case, curved slots such as 770 are formed through the sides of each toroid to implement flux switches A to D. The magnetizable member in this embodiment is implemented with a block of material 704, preferably the same high-performance magnetic material used to construct loops 400, 401. Permanent magnet 702, shown at 702, preferably has the same length as block 704, enabling the various constituent parts to be held together with compression, shown in Fig 7b. The following sections summarize some of the important characteristics of the preferred embodiments. In terms of materials, the apparatus benefits from the use of nanocrystalline material with a square BH intrinsic curve, a high BR, remanence, which is about 80% of its BS, saturation, a low HC, coercivity, and a fast magnetic response time to saturation. An example is fine metfeet, 3H from Hitachi of Japan, which has a BR of 1.0 Tesla, AB, saturation, of 1.21 Tesla, a time to saturation, BS, of 2 microseconds, and an HC of 0.6 amp turns per meter. Modern permanent magnets are used with a square BH intrinsic curve, a BR in the range of 1.0 Tesla or more, and high HC in the range of 800, 000 amp turns/meter or more. An example is the neodymium iron boron magnet from the German company VAC, which has a BR of 1.427 Tesla and an HC of 1,079,000 amp turns per meter. An important consideration is the matching of the magnet to the nanocrystalline material, both in Tesla rating and in cross-sectional area. The magnet's BR should be below the B saturation of the nanocrystalline material. If the magnet is too strong for the nanocrystalline material, this may cause the nanocrystalline material to saturate at the area of contact with the magnet. The current driving the reluctance switches in the prescribed 2x2 sequence should have a sharp rise in the leading edge, Tr, of each pulse with a pulse width, Pw, and amperage value that are sustained until released at the end of the pulse width, Tf. The table below shows the effects of input current pulse rise times, Tr, on the output. There exists a narrow band of Tr, before which there is small power output, at which there are excellent power output and coefficient of performance in the range of 200 to 400 or greater, and after which there is no major increase in power output. The coefficient of performance of this device without the coupling circuit is defined as output power divided by drive power for the switches. 10 microseconds. Output power 15 kilowatts square waves after one cycle.